I don't think you're 100% sorry, but I think you're a little sorry.
I'm sorry to you.
Okay. All right. Okay, all right, let's get started. Homework 2.2 is still being graded. I just got my TA live on Blackboard, so he's going to chip away at that, and probably homework 2.3 this weekend to get that ready for y'all for Wednesday. But the solution should be available for homework 2.2, so you can review that. Like I said, I'm going to assign homework 2.4. There's only one problem, so up until now I've been giving you 2 reactions problems per assignment. This one I'm only giving you 1 because reactions with internal hinges, as you'll see, are just a little bit more involved. Globally, I don't think it's any more work than the other assignments. And I want to be clear, I don't want to be the guy who's like, ooh, you have 3-day weekend, I'm going to give you more work. I'm trying not to do that, but I'm not. At the same token, I'm not going to give you something that's due Monday. It's a break. I'm taking the break. So yeah, there are a couple of assignments that are going to stretch across a couple of lectures later on in the semester, and that's simply because they are long. And there's sort of no way of getting around that. And that'll become clear when we get to those points. But primarily, those assignments involve deflections. Deflections just take a little bit longer to do. Okay, any questions? All right. We're going to get into our, wrong PowerPoint. We're going to get into our discussion of hinges again. And I'm going to really quickly go through these slides because I want the bulk of today's lecture to be focused on our example problem. So in this section, what we're dealing with is our final concept with reactions, and that's how to deal with internal releases such as hinges and utilizing our tool of cutting a section. And to be clear, look at this list. Just in 3 lectures, we've covered all of this. You know what I mean? And the idea is that each little piece is just another component that we add to our skill set. You know, first we dealt with just concentrated loads. Well, then we added distributed loads. Then we added inclined loads. And we added concentrated moments. And so we've added different boundary conditions. First we dealt with simple. Then we dealt with inclined rollers. Then we dealt with fixed support. So the idea is that as we start adding this stuff, we can handle more and more. Today, what we're going to focus on are problems with internal releases. So one of the things you'll find right off the bat, for problems that are statically determinate, that have internal releases, they are going to have more than 3 reactions. Okay? So up until now, we've had problems that have only had 3 reactions. The one we're going to deal with today has 4. Okay? Because there's 1 hinge. And if there were 2 hinges, there'd be 5 and 6 and so on and so forth. So depending upon the number of hinges that you add. So right off the bat, internal releases, in order to maintain static determinacy and stability, we're going to have to add another reaction. So we're going to be dealing with more unknowns. What the hinge gives us is a known, right? So, you know, our secret weapon of structural engineering is the samurai sword or the lightsaber if you happen to be a sci-fi fan. Hopefully you enjoy the Star Wars images there. I've got some lectures later that have Link and Mario in them. So, again, I'm hip with the kids and whatnot. The least hip thing I could have ever said. I love my job. Okay, so what we're going to be doing in order to deal with internal hinges and to deal with these extra unknowns is we're going to cut a section, okay? And so what that means is, as we said last time, whenever you cut a section through an arbitrary point in a structure, you have at most 3 unknowns. Just as you do with equilibrium across the structure overall, you have an unknown component in the x direction, unknown component in the y direction, and an unknown moment. And you solve for those 3 unknowns using the 3 equations of equilibrium like you would if you were solving for the reactions as a whole. The beauty of a hinge is that when you cut a section through a hinge, you know what one of those internal components are. You know that the internal moment is 0. So you can cut a section, some moments at that hinge, and then determine unknown reactions as a result. And in order to explore this, I do want to say one quick thing about our sign convention. This isn't going to matter a whole lot right now. When we get into particularly shear and moment diagrams, it's going to matter a lot. For trusses, the only thing that's really important is that we're going to consider axial forces that cause tension to be positive, but, and I want to try and say this carefully, being super, super rigorous with this sign convention is not the most important thing in the world when you do a truss analysis. What is important is that you're just maintaining consistency in your analysis between what's tension and what's compression. In other words, if you were doing an analysis and you assumed tension would be positive, like we have here, that's fine. If you were to assume compression is positive, that's fine too, as long as you're consistent, okay? That probably don't really know what I mean by that. That'll become much more important when we look at deflections. Like when you do a deflection analysis, you have to actually analyze the truss twice, and as long as you're consistent with whether or not tension is compositive or compression is tension is positive or compression is positive, as long as you're consistent in your analyses, you'll get the same answer. It's just all about being consistent. One of the reasons I do kind of go on this tangent a little bit is that there are some software programs that have different sign conventions when it comes to columns. So for example, a very popular software program for structural analysis is RISA, and RISA will assume compression is positive because it's thinking about it from a building design standpoint. So when you're designing buildings, you're designing beams and columns. They just want to know what the compressive force is in the column. Whereas general purpose finite element codes like MASTAN or maybe some of your more I would say higher level ones like Abacus or ANSYS or whatnot will typically assume tension is positive. So you just need to be consistent with what you're doing. Again, that'll become more important a little later. This is the star of the show today. This is an intricate, complicated problem, or at least it seems to be. But I promise you this structure is no more challenging than the previous ones that we've done if you develop the idea of cutting a section. Okay? So I'm going to pull the notebook up and I'm going to give you a sec to copy this down, then we're going to handle this. I'll make this kind of big so we can all see that a little better. I'll give you all a second to copy that down. Okay. So the first thing I want to do is let's identify these reactions. And I'm going to go ahead and tell you, for some of these problems, it's going to make a lot more sense to just assume that they're all upward, okay? And I want to be clear that for this problem, and it just so happens to work out for this problem, they all end up being upward. But that might not always be the case, okay? It's very possible that some of these reactions act downward, and what I have found when you start dealing with this many unknowns, it's just easier to blanketly assume they're all upward. So if you get a negative answer, you know what the context is. All right, don't forget we also have AX right here, and this we can deal with. We can deal with this right now. I think that one's pretty easy, right? There are no lateral forces, there are no horizontal forces, so I know that AX is 0. Now, for our distributed loads, let's collapse those. So we'll start at the left, work our way over. So over here, I have 2 kips per foot over a distance of 15 feet. So that collapses into a concentrated load of 30 kips. And then from A, I think that's 7.5 feet. I think that's pretty simple. Okay. What about this triangular load? I have a triangular load that's 15 foot long and goes from 0 to 4 kips per foot. So 4 times 15 over 2. Don't forget it's a triangular load, so we need to divide by 2. Collapses into a load of, I believe again, 30 kips, right? And then this dimension here is what? 5 feet. Okay. Finally, we have 1.2 kips per foot. And that's over a distance of 15 feet. So we can collapse that again. What's the magnitude of that load? 18 kips. And then the distance is 7.5. Now I want to take a step back and just make one point. If you can analyze this, you can analyze just about every potential real world scenario that will get thrown at you. And I'm leveling with you. Some of the problems that we do in here stretch reality a little bit. I'm not lying. Okay? I don't think I've ever met a structural engineer who had to actually design a beam like this. But the idea is that if you can handle this, you can handle anything that you're getting in the real world. So I want you to understand that what we're doing in here, I am trying to ground in reality as much as I can. Even though I might give you a problem that's kind of wonky, you could do this, you can handle anything analysis-wise in the real world. Okay. Now, I want to begin this problem by handling it the way I would any of the problems in the past. Okay? So I'm going to sum moments a day. Done before, right? Some moments a day to get some reactions. So let's see what happens. So let's sum moments a day. Let me scroll down a little bit. Let's just see what happens. Let's just go through the motions. So do I have to consider AX? Nope. Do I consider AY? Nope. What about this first 30 kips? Goes on the left side. And that's a moment arm of what? 7.5 feet. So what's next? I got a 14 kip load. That's at a moment arm of what? 15 feet. Okay, BY at a moment arm of 30 feet. Okay. What about this next 30 kips? What's the moment arm for that?
35 feet.
35 feet. There we go. We've got 18 kips. What's the moment arm for that one? 15.
52.5 feet.
Say it again.
52.5 feet.
There we go. And then we have CY over here times a moment arm of what? 60 feet. Okay. So, it's interesting. First off, let's add up everything over here. So what do we get when we handle this column? 30 times this, 14 times this, this times this. Add it all up. What do we get over here?
2,430.
2430. Do I have a second on that?
Yeah.
Okay. Equals BY times 30 feet plus CY times 60 feet. That's different, isn't it? We haven't had that before, have we? I mean, normally what we've done is when we go through in some moments, we get 2430 equals BY times 30, and we solve for BY and we move on. But that didn't work out here. We've got two terms. This didn't tell us what BY was. This doesn't tell us what CY is. But it gives us a true expression. We know that that times 30 plus that times 60 equals this, but it doesn't solve each one of them independently, right? So we're kind of left with more questions. Here's what I'm going to do. I'm going to indicate this as equation, or maybe I'll shorthand this. I'll say EQN. Equation 1. So that's true, but it doesn't tell me anything. Let's just leave that one alone. Okay, so we sum forces in the x direction. We sum moments. Let's sum forces in the y. Let's just do that. Now this is easy. If I look at my structure, what do I have going up? AY, BY, and CY. What do I have going down? Well, I got 30, 14, 30, 18. So, AY plus BY plus CY equals, was that 30 and 30, 60, 14 and 18, 32, was that 92? Damn, I kind of have the same thing happen again. I don't get an answer. I get an expression that compares some of my unknowns, but I don't actually get my unknown. So, let's call that equation 2. And let's think, now what do we do? Well, we haven't broken out the secret weapon of structural engineering, the samurai sword or the lightsaber if we happen to be a sci-fi fan. What I know about this structure in regarding its internal response is I know that the internal moments at that hinge are 0. Okay? Now, in order to determine internal response, we cut a section. Now, where I cut the section, I think is going to be pretty straightforward. I'm going to cut it through that hinge. Okay? So, typically what I'll do whenever I cut a section, here, let me move this up a little bit. Or, tell you what, better, I'll just put this 7.5 feet over here. So, typically when we cut a section, what I will do is I will sort of draw my line, and then, like you'll see on a CAD drawing or something like that, I'll do section 1-1 or section AA or something like that. So that's where I'm samurai swording or lightsabering through this section. Okay. Now, when you cut a section, now I want to make sure that everybody understands this. When you cut a section, it analytically does not matter which direction that you look. In other words, when you cut a section, you are splitting this structure up into 2 separate free body diagrams. It does not matter if you assess the free body diagram on the left or the free body diagram on the right. You will get the same answer. The math will work out. But just because the math works out, you know, the structure doesn't care which way that you look, just because that's true doesn't mean that we shouldn't have a little bit of common sense about how we address the problem. Let's just look at this section cut. Which looks like it's the easier direction to look? Left or right?
Right.
The right. For 2 reasons. One, there's 1 unknown reaction to the right as opposed to 2 unknown reactions on the left. That's probably the most important. But on top of that, there are simply fewer loads on the right than there is on the left. So I'm going to cut a section and I'm going to look to the right because it's easier. Okay? So in order to do that, what we're going to do is we're going to go down here and we're going to say cut a section at the hinge. So I'll use my @ symbol. We'll say look to the right. So now I'm going to redraw this free body diagram a little bit. So let's see what we got. We got Here's the beam. Here's our hinge that we cut the section through. Now I have a roller right here and a vertical reaction at that roller, which I'm calling CY. I don't know what that reaction is yet, but I did assume it was upwards. I have my distributed load, which, let me take this diagram. The beauty of doing this on a screen as opposed to a whiteboard, you can just start to move it. So this is 1.2 kips per foot, okay? There's my section cut. And then we collapse that into that collapsed point load, which I believe was 18 kips. And then let's put some dimensions on this. We said that this was 7.5 feet. And then we have this dimension here is 15 feet. Okay. The last thing that I need to, so would you agree, did I account for everything that's on, here, let me scroll up a little bit. Did I account for everything that's on the right side of that section cut? I've got the distributed load, the reaction. I mean, honestly, imagine if this was a whiteboard and I just took my eraser and erased everything over here. That's what I would have left over, okay? The other thing is I need to indicate those unknown forces inside the structure at the hinge. And so what I'll do is I'll call those, I don't know, Fy, and we'll call that Fx. Now, I'll go ahead and tell you, I have drawn those in the direction of their positive sign convention. If I were to have drawn them in the opposite direction, it would not affect what I'm about to do. So right now, I don't want you to get too worried about that. But later on, that will become important. And when that becomes important, we'll definitely be pretty rigorous about that. The other thing I will point out is that when you're doing your homework assignments and doing your exams, what I have found trips students up the most during calculations like this is simply failing to draw this. Like, I don't have time for this. I don't want to draw it. I'm lazy. I'm not going to draw it. And by not drawing it, by not actually taking the time to sketch out the structure, to sketch out all the components, when you start summing moments, you have errors. Take the time to draw it out. I promise you it will pay dividends down the line. Okay, so the reason for cutting a section and looking to the right is if I look at this free body diagram, now imagine that this was a completely separate structures problem. Couldn't I sum moments here to determine the reaction at C? Because these two are going to go right through the hinge, right? So that's the whole point of the analytical tool of cutting a section, is that by cutting a section and looking here, I only have one unknown. And that's what the hinge affords me. I know that if I sum moments at that hinge, they are going to be zero. That's the value, yes.
The reason we don't include a bending moment reaction is because it's a hinge.
Because it's a hinge. We know there's no internal moment at a hinge. You're exactly right, okay? If I were to cut a section at any random arbitrary point, there would be a moment. You are 100% right. We will also find this when we draw moment diagrams for structures with hinges, we will find that the moment diagram crosses zero at the hinge. Cool. We will find that. It'll be a check for us to see whether or not we're doing it correctly. So, all right. So what I'm going to do is, here's how I sort of write this. I say we're summing moments, and I put the hinge, and then I usually put a little arrow like that. So this is like summing moments at the hinge looking to the right. Equals zero. That's kind of what I mean by that. And then if I do my little table, what do I have? I have 18 times 7.5, and I have CY times 15. That's it. So boom. That's all there is to it. So 18 times 7.5 is 135. So therefore, CY is plus 9, I think. Did I get that right? Yeah. And I think that, yeah, if 18 times 7.5 equals 9 times 15, yeah, I mean, you can kind of make that analogy. Pretty simple, right? Notice how 9 came out to be positive. Keep that in mind. 9 is positive. So what do you think we ought to do with that reaction? I'll give you a hint. It's on the screen right now. There you go. So we take the 9, plug it into equation 1, and that'll give us BY. Then we'll have BY and CY, plug it into equation 2, we get AY. See? Not too bad, right? So now what I'll do is I'll say back to equation 1. So BY times 30 feet plus CY times 60 feet is 2430 foot kips. So BY times 30 feet plus 9 kips times 60 feet is 2430. So what does BY end up equaling when it's all said and done? Because all you do is you take 9 times 60, move it over here, divide by 30. What do we got?
63.
63. Do I have a second on that?
Yeah.
Okay, so plus 63 kips. 63 kips upwards. And now, see how this is positive and that is positive? So now we take positive values of 63 and 9 and plug it into our equation 2. So we can say back to equation 2. So AY plus BY plus CY is 92 kips. So AY plus 63 kips. And if it ended up happening that one of these was negative, I could just plug in a negative number. You know, because the math, again, I had a consistent assumption at the very beginning. And so AY is positive, I think. And I think that's 20. 63 and 9 is 72. So 72 off 92, yeah, 20. So 20 kips. 20 kips up. So AX is 0. AY is 20. BY is 63. And CY is 9. What do you think? That's not too bad, right? See, this is my point. Like, look at the problem at the very beginning. Didn't the problem at the beginning kind of look like a nightmare? Really isn't, though. That's kind of the point. It's really not that hard, you know? You're just applying fundamental principles of statics and your secret weapon, and that's all there is to it. So, yeah, it's a little longer than some of the other problems, but it's not hard. Now, the problem that I gave you on your homework assignment is a frame, and it's a portal frame. So a portal frame just looks like up, 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 and then there's a hinge on the corner. So you can like cut a section and then sort of like look down. So. Any questions? All right, I want to talk a little bit about our next topic in the class, but I'm not going to take up too much of your time because I am going to let you go a little bit early. But I want to introduce the next topic And I'll explain why. Don't need Teams right now. Okay, we'll say allow access, but I don't need it right now. Okay. I want to at least introduce some of the ideas behind trusses. And the reason I want to at least introduce this is because one of the things about trusses, at least in this class, the examples are kind of long. They're not hard, but there's a lot of drawing and a lot of calculation. So I don't want to get into a time crunch when we come back on Wednesday. So I at least want to talk a little bit about trusses in general. And particularly, we're going to focus on plane trusses. So those are trusses that are idealized in 2 dimensions. I want to at least take a step back and have you understand where, what a truss really is and where you find that they're broadly applicable. So trusses, if I wanted to give you a basic definition, they are arrangements of straight elements in triangular patterns to form a structure, or a component of a structure. You tend to find trusses applied in 2 primary areas. The first is bridges. You tend to find trusses just being used to develop bridge structures, but also roof systems. Okay. The advantage of a truss from a structural standpoint, so I do want you to understand, or let me go back. I want you to understand when you would use a truss and when you wouldn't use a truss. So trusses are, from a structural standpoint, very lightweight and very efficient. And what I mean by efficient is that you get a lot of structural stiffness for very little weight. Okay, so stiffness is the relationship between applied forces and resulting deformations. And pound for pound, trusses are among the most stiff structural systems we can employ. So they do have advantages in that regard. So if you ever have a structural challenge where you need to achieve a very large span with nothing under it, trusses tend to be a viable solution in that regard. So for example, for this bridge here on the right, we have a really large span and we don't want anything under it to impede the water flow. So that's why they're using a truss. For architectural considerations, trusses tend to be used for roof systems for 2 reasons. One, trusses by their very nature tend to have potentially sloped roofs, which allow for drainage of rain and whatnot, so we want that slope whenever feasible. But second is architects tend to like really open spaces. And so there's another challenge where you want a really, really large span. You need a structural element that can resist that span. That's where trusses come into play. Now, where's the disadvantage of trusses? I'm curious. I've given you a bunch of advantages. What do you think is the disadvantage of trusses? Curious.
It's a lot of material.
It's a lot. Well, it's not so much that it's a lot of material, because actually pound for pound, I bet you trusses are lighter than their being counterparts. It's not the material. They're expensive. Trusses take a lot of drilling, a lot of fabrication, a lot of potential welding, a lot of cutting. They are complicated. They take a long time to put together. They take a lot of man hours in the fab shop. So they are expensive. Okay, so you are only going to use trusses in areas where there's a clear benefit. Okay, so I want you to kind of understand as structural engineers when you would use them and when you wouldn't. Okay, now some assumptions for truss analyses, and we're going back to statics land with this. So there are really 3 core assumptions that we make when we analyze a truss. Okay, and I want to explain what each of these assumptions really mean. Okay, so the first one is that all members are connected by frictionless joints. And so what that is intended to convey is that when you apply a load to a truss joint and you analyzing it using the method of joints and method of sections, you can be confident that those results are representative of the only forces that you need to consider. In other words, if there was friction or some sort of lack of fit or something like that, you might get some unintended bending moment or some unintended shears in the truss elements. What this assumption is basically saying is that those values are so small that you can disregard them. Okay? The second is that all loads and support reactions are applied only at the joints. That is intended to ensure that when you are analyzing the structure, the loads are going directly to the joints, so they are only experiencing axial forces. Again, no shears, no moments. And the third assumption goes to that effect as well. So the third assumption says that at each joint, the centroidal axes of each member coincide. So the idea is that here's a truss joint, okay? This member, let's say this member over here on the right, it has a centroid, probably, I don't know, something about like that, right? This member has a centroid, this member has a centroid, this member has a centroid, this member has a centroid. The idea is that all those centroids meet at a common point. And that's not even just an assumption. We do that in the real world, in fabrication land. So if you're looking at steel trusses or even large wooden trusses, they will fabricate them such that the centroids all meet at a common point. And again, that's to reinforce the idea that these truss elements should only be experiencing axial load. Okay? And again, the point of that is to reduce the shear and moment in the members and in the connection. So the idea then, from a mechanics perspective, is that if those three assumptions hold, if we're looking at an arbitrary structure and you cut a section through a member in that arbitrary structure, you have unknown shears, unknown moments, unknown axial forces. However, when you cut a section through a truss member, because of those three assumptions, we can rest assured that there are only axial forces in the member, and that's it. Because we are fabricating them that way, and we are loading them that way so that that won't happen. That's kind of the point of this. It's one of the reasons why trusses tend to be sort of a little bit in their own class from a structural analysis standpoint. They are their own unique animal. Whereas beams and frames are a little bit more general, and they have a little bit more going on in terms of shears and moments and what have you. Now, the two methods for analyzing a truss are the method of joints and the method of sections. Okay? Now, I can tell you that in this class, we are going to spend the bulk of our time dealing with the method of joints. Okay? The reason why is because of what their uses are. So, the method of sections is intended for spot checking and for quickly determining the forces in particular members of a truss, right? So here's a truss, I've got this big truss, and I want the force in that member. The method of sections works great for that. We're more often than not interested in the force in one member. We want the forces in all the members. And we are going to need them for a number of reasons. So first off, as a designer, if I want to design the truss, I need the force in every member. A force in one member doesn't help me. I need everything. The other thing is that in order to compute deflections, I need the force in every member. And that'll become more important or easier to understand later. So the method of joints is really what we're going to spend most of our time on. The method of joints in this approach, we take each joint one by one, assess its equilibrium, and then determine the unknown forces in those members required to achieve that equilibrium. The method of joints is tedious, I won't lie to you, but it's thorough. It will work to get you the forces in the entire structure, and that's why we're going to spend most of our time on it. Whenever we're dealing with the method of joints, remember, we made some assumptions. We made assumptions that all the centroids of the members all pass through a common point. We made the assumption that all the loads are applied directly at the joint. We made the assumption that there's no friction or unintended forces. What those assumptions mean is that we, unfortunately, well, I guess fortunately or unfortunately, depending on how you look at it, but what those assumptions mean is that we are short one equation of equilibrium. If you go back to Engineering 213, one of the things that we did in statics is the first thing that we dealt with were statics of particles. In other words, situations where all the forces all met at a common point. And so we dealt with sum of forces in the x direction, sum of forces in the y direction. We didn't start considering the sum of moments until we dealt with situations where the forces don't meet at a common point, where the forces are non-concurrent. Okay? So what that means is when we're dealing with the method of joints, we only have two equations of equilibrium for each joint. The sum of forces in the x direction, the sum of forces in the y direction. So when we utilize the method of joints, we can only solve joints where there are at most two unknown forces. So, for example, this is going to be a weird truss to throw at you, but I kind of want to make a point about this. And we're going to talk about this later. But let me show you something. So here's a, this thing doesn't like me. Let me show you a weird truss. Okay, so let's say there's a truss like this, and the truss has 4 joints on the corners, right? Now let's say there's members on the ends, but let's say there's a member like this, and a member like this. And let's put a hinge and a roller right here. God, that's horrible drawing. This is a very interesting truss in that this truss is statically determinate externally. In other words, I could put loads on it externally all day long, and I could solve for the reactions. But internally, it's indeterminate. I cannot solve the truss indeterminately. Because if I look at this joint, there's 3 unknowns. A member here, a member here, a member here. What about this joint? 3 unknowns. What about this joint? What about this joint? This is internally an indeterminate truss. Remember that IE formula? Remember how I said IE was the definition of external indeterminacy? So later on we're going to look at internal indeterminacy, whether or not a truss can be solved through the method of joints or method of sections. And if not, how do we deal with it? We're going to get to that, later on. Okay. What we're going to do starting Wednesday is we're going to start dealing with problems with the method of joints. Now, I'm not going to start this problem today, but I want to show you something. Notice what I gave you in this problem beyond just the truss. I gave you the reactions. At this point, are we good with that? I want the examples later to be focused on the topics that we're dealing with later. So you're going to find situations like this where I just give you the support reactions because at this point you should be able to compute them, right? We could go through them if you would like, but the idea is, look, some moments here, 10 times 6, 20 times 12, 15 times 8 has got to equal something times 24, that's 17 and a half, so on and so forth. 15 to the right, 15 to the left, and then some verticals get 12 and a half. So there's going to be problems later on where I just give you the support reactions. I hope that's okay. I'm more than willing to go through them if you would like, but I want to get to the good stuff. I want to get to what we're talking about, okay? So I just wanted to forewarn you of that. Sound good? We're going to begin this example on Wednesday, but for now, I'm giving you 6 minutes of your life back. You all have a wonderful 3-day weekend. I'm going to stop the recording and bring the QR code up in case anybody needs it. That's all I got.